Hey everyone, let's do the practice problems for lesson 7 together. So practice 7.06.07, whatever Desmos likes to call it. Let's do this one together today. So I've already got the warm-up screen up, and it says select all of the expressions represented by the tape diagram. And when I look at the tape diagram, I see 3 boxes or sections, whatever you want to call them, here, here, and here, and each of them has an x plus 5 in it. And so the way I like to think of that is 3 quantities of x plus 5, right? There's 3 of these things, and each of one of them is worth x plus 5. And so the way you write that mathematically is you want 3 times x plus 5, right? Anytime you have 3 of something, you just multiply it by 3 to represent that. And you would do it with parentheses. You would write 3 times not just the x and not just the 5, but both. So that's what it means when you put stuff in parentheses like this right next to a number. It means 3 times the whole thing. And so if we can find this as an option, I know that's going to be one of the ones I'm going to select. And I believe that's it right there. Oops, no, that says 3x plus 15. Hold on, I don't want that one. I want the one right above it. 3 times quantity x plus 5. So I'm not going to select the one that says 3 times x plus 15, because if I were to use the distributive property, when I multiply that 3 times the x, I get 3x, that's great. But when I multiply that 3 by the 15, I would get 45. That's bigger than what I want. Let's see here. Here we got x plus x plus x, so 3 x's, that's good. And plus 5, oops, I didn't mean to make that line. And then plus 5 plus 5 plus 5. So you got 3 x's and 3 5s. That's the same thing I have in the tape diagram. It's broken up differently, right? That would be like as if we had 6 boxes, 1, 2, 3, 4, 5, and 6, and it went x, 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 5, 5, 5. But those are the same thing. And in the end, it's all the same pieces being put together. And so I would say that this is equivalent. And then this next one is literally the exact same thing as the first one I circled, except the 3 is on the back end instead of the front. But you're allowed to do that, right? You can take multiplication and switch them. This is called commuting them, or in other words, we're using the commutative property that says we can take a number, multiply it by 3, or multiply 3 by that number. We're going to get the same answer either way. So that's another good one. This one here is what you would get after using the distributive property on the first one I wrote. See, this right here means 3 times the stuff in the parentheses. So 3 times the x and 3 times the 5. And math teachers usually like to draw these arrows to show that they're like distributing the 3 to the x and distributing the 3 to the 5. That's why we call it the distributive property. And so 3 times x is 3x, and 3 times 5 is 15. So we get 3x plus 15, and that's what we have right here. It's written differently. It's 15 plus 3x, but it doesn't matter. The last one, though, nope, I would not select that. 3x plus 5, that's not the same as 3x plus 15. That's the sort of thing that would come from a student making a mistake doing the distributive property, is where that one would come from. All right, let's move on to the next. It says solve the equation by filling in the blanks. Okay, so what the blanks here are is the new equation you get after each time you do what I would call a solution step, or sometimes people call a properties of equality step in solving this equation. See, when I look at this equation, the first one here, well, I look at what's happening to my variable. I see that it's being multiplied by 15, right? 15 times x here. And then I see that 10 is being subtracted from it. When I solve equations, I want to use the opposite of the operations I see happening to my variable. So where I see minus 10, I know I'm going to need to add 10. And where I see my variable being multiplied by 15, that means I'm going to need to divide by 15. We're always like working backwards to try to undo these equations. So my first step in solving this would be to add 10 to get rid of that minus 10, right? Plus 10 and minus 10, they make a 0. But if you do it to one side of the equation, you must do it to the other side of the equation. That's how these things stay balanced, equal, fair, true, whatever you want to say. So I'm going to add 10 to this 65 over here. And so what happens is this minus 10 and plus 10, they make a 0, they go away, but we still have our 15x left over here. So that's why it's there. On the other side, I've got 65 plus 10. That's going to be 75. So the new equation that came from doing that step is 15x equals 75. And so now I know that whatever my number is, if I multiply it by 15, I get 75. Well, that just means if I take 75 and I divide it by 15, I should get what my number is, right? So I want to do, 75 divided by 15. But if I do it to one side of the equation, I must do it to the other side. That's how they stay true. And what happens here is I have 15 times my number, but then I'm also dividing it by 15. Those things like undo each other, and I'm left with just x. And then on the other side, 75 divided by 15 is 5. So your first blank should be filled in with a 75. The next one should be filled in with a 5. And we're moving on. All right, so another equation to solve. And I notice that the first thing in the second line here, or basically I notice that the second line here is just x plus 7. And so that's a big clue for me on like what I'm supposed to do here. Because when I look at the previous line, it also says x plus 7, except there used to be this 3 here. There used to be a 3 right next to the parentheses, and that means 3 times the stuff in the parentheses, right? 3 times x plus 7. And so when I'm solving equations, I'm always doing the opposite of the operation I see. If I see 3 times x plus 7 and I want to get rid of that, then I need to divide by that 3. This time I'm going to use a fraction bar to mean division instead of a division symbol. So I put that fraction bar under that entire side of the equal sign. I kind of drew it too long, to be honest. It shouldn't be under the equal sign like this. Oh, shouldn't erase the whole thing. But I put my fraction bar, which means division, under this whole thing. But what happens is this 3 that's multiplying and this 3 that's dividing, they create like a 3/3 fraction, right? 3/3, which is just 1. And so, well, a 1 in multiplication just goes away. It doesn't really mean anything. So we're left with just x plus 7. But if I divided the left side of the equal sign by 3, I must divide the right side of the equal sign by 3. And I get negative 12 divided by 3 is negative 4. All right, and then in my last row here, all I have left is my x. We call that an isolated variable. Well, what I had in the previous line was this plus 7. I got to get rid of that somehow, right? I use the opposite operation. To get rid of a plus 7, I'm going to minus 7. But if I do it to one side, I got to do it to the other. So let me subtract 7 from that negative 4 as well. But don't mess this one up. You've got negative 4 minus 7, but subtracting 7 is the same as adding negative 7. And so this is going to equal negative 11. Next. Okay, this one says negative 100 times my unknown number, x, minus 100 equals 0. Okay. Well, I noticed that in the second row here, the minus 100 part is gone, right? So the only way somebody could have got rid of that is by doing the opposite operation. So they must have added 100. Because that minus 100 and that plus 100, they're going to create a 0 on the left side of the equal sign. But on the right-hand side of the equal sign, I have to do the same thing. If I add 100 over here, I have to add 100 over there. So let me write plus 100 here. So these two things right here, they cancel each other out. They're gone. But the 0 plus 100 creates 100 over here. So our new equation is negative 100x equals 100. In the last row, I have an isolated variable, x just by itself. So they got rid of the negative 100 that was multiplying by x. The only way they could have done that is through an opposite operation. I need to divide by negative 100 in order to get rid of that multiplying by negative 100. But if I do it to one side of the equal sign, I must do it to the other side of the equal sign. That's why people say divide both sides by such and such, or add such and such to both sides. It's just another way of saying, hey, you do it to one side, you got to do it to the other. And so what we're left with is 100 divided by negative 100. That's just negative 1. So in this case, x is negative 1. All right, let's keep it moving. Solve each equation. Okay. No big deal. I'll write them all out for you. I'll use a different color on each one. I'll do them all in different spaces here. So the first one, we got negative 4x equals negative 28, or in other words, negative 4 times my unknown number equals negative 28. This is called a one-step equation because it's only going to take us one step to solve. There's only one operation happening to the variable. It's being multiplied by negative 4. So I'm going to do the opposite operation. I'm going to divide by negative 4. I'm going to use a fraction bar to represent division. If I do it to one side, I must do it to the other side of the equal sign. And what I'm left with is x, because this negative 4 divided by negative 4, they just create a 1. So really what this says is 1x, but nobody ever writes the 1, equals, okay, 28 divided by 4 is 7. And a negative number divided by a negative number is a positive number. So it's positive 7. So there's your answer for that first one. Okay, so the second one says negative 4 times x plus 1 in parentheses. So you got to multiply the negative 4 times the x and the 1 equals negative 28. So there's two strategies you could use to solve this equation. We saw one of the strategies on a previous question in this video, so I'm going to do the other way. I'm going to use the distributive property first. I'm going to distribute negative 4 to x and negative 4 to 1, and that means to multiply them. And what I get is negative 4x plus negative 4, because negative 4 times 1 is negative 4, equals negative 28. Okay, so now I'm going to use some opposite operations. Here I'm adding negative 4, so let me add positive 4, right? The whole point is to make a 0. Negative 4, positive 4, they combine, make a 0. If I do it to one side, I got to do it to the other. Oops, that's supposed to be a 4. And so what I have now is negative 4x, right? These go away, but this comes down, equals negative 28 plus 4 is negative 24. Now I need to divide both sides by negative 4, right? Because I'm trying to get rid of this multiplying by negative 4 here, but I got to do it to both sides. And what I'm left with is x equals 6. Sorry, my work got all diagonal there. I wasn't expecting to use that much space to solve that one. All right, let's see. Let's use orange for the next one. Next one's a little bit easier. X plus 7 equals negative 1. This is another one-step equation. There's only one operation happening to my variable. It's being added to 7. So let me subtract 7 to get rid of it. But if I do it to one side, I must do it to the other side. And so I get x equals 1 minus 7, negative 8. And last but not least, let's see here, what color have I not used yet? How about this one? Negative 3x plus 7 equals negative 1. Okay, I look at my variable, I see that it's being multiplied by negative 3, and then I see 7 is being added to it. So that means I'm going to need to subtract 7 and divide by negative 3. So let me do those. Subtract 7 from both sides. I get negative 3x equals negative 8. And divide both sides by negative 3. This bar right here is supposed to be a division bar. That's my -3. And I get x equals 8/3. Right? So the negative sign on top and bottom, they just sort of cancel each other out. A negative divided by a negative just makes a positive anyway. And 8/3, I just write it like that. You can put it as a decimal or whatever, but I'd rather just leave it as 8/3. I'm surprised they would give us an improper fraction answer like that, so I'm just looking at it to double check. Did I get that right? Oh wait, I got the answers down here. Let's see. Yep, that last one's supposed to be 8/3. Looks like we got them all right. Okay. All right, so we got to match the equations to the story type thing. I think it's easiest to read the stories and then find the equation that goes with it. So I'll start here. A baker uses 4 cups of flour. She uses 1/4 cup to flour the, she uses 1/4 of a cup to flour the counters. Like you sprinkle flour on the counter so you can put dough or whatever there and it doesn't stick. And the rest to make 8 muffins. Okay. So you got 4 cups of flour total, or no? Yeah, that's the way I read it. It reads to me like she's got 4 total cups. 1/4 gets used to make to flour the counters, to sprinkle, and then that makes a total of 8 muffins. Okay, which one of these goes with that? Ah, okay. I think it's this one. This is hard. I actually had to think about that for a second. So the reason I choose this one is because the amount of flour is that each cupcake or muffin, I guess, each muffin needs is our unknown, right? So X for this story is the flour per muffin. And when I look at this equation, I see that X is being multiplied by 8, which is good, right? The amount of flour per muffin multiplied by 8 because there's 8 muffins. And then it says plus 1/4, right? That's that 1/4 of flour that was used to sprinkle on the counters. And all together, that's supposed to equal this 4 here. And that sounds right to me. 8 muffins worth of flour plus the 1/4 cup that got sprinkled on the counter equals the 4 total cups the baker used. So I'm rolling with that one. All right, next, let's do this one here. It says a stack of nested paper cups. So it's like, the cups inside the cups, like when you buy them in the store, is 8 inches tall. The first cup is 4 inches tall, and each of the rest of the cups in the stack adds a 1/4 cup into the height, right? So like if you take just a singular cup and maybe you put it like face down on the counter, it'd be 4 inches tall. But then when you stack another one on top, it doesn't make it another 4 inches tall, right? It just adds a little bit of height to it because it's like almost sitting perfectly on it. So first one's 4 inches, and then each one after that is another 1/4 inch, 1/4 inch, 1/4 inch, 1/4 inch, 1/4 inch, 1/4 inch. And the total stack height is 8. And so I think this is the one I would go with on this one. And the reason for that is the first 4 you see in this equation, that's the original 4 inches height of the first cup, right? And then X in this equation represents the number of cups stacked on top of the first one. The first one doesn't count because the first one's just that original 4 inches. So stacked on the first one. So the second cup and beyond are all represented by X in this case. And so if you look at the equation here, it says 1/4 times X, right? Which is what we want, 1/4 of an inch multiplied by however many cups that is until we get to the total of 8 inches, which is on the other side of the equal sign. So that's what we want. So by process of elimination, I'm going to say that these two probably go together, but let's read it anyways. It says, Mariana has an 8-foot piece of ribbon. She cuts off a piece that is 1/4 of a foot long and cuts the remainder into 4 equal pieces. And that makes sense. See, the length of the pieces is X. Multiply that by 4 because there's 4 of them. Add that 1/4 inch or 1/4 of a foot that she cut off for whatever reason, I don't know why. And they all should add up to the 8-foot piece of ribbon that she started with. All right, next one, slide number 7 or problem 4.1. There are 88 seats in the theater. The seating in the theater is split into 4 identical sections, okay? Each section has 14 red seats and some blue seats. Draw a tape diagram or hanger to represent this situation. Okay, so this whole unit is about algebra, expressions, equations, using variables. They need me to use a variable somewhere in here. And the thing that I don't know, even though you can probably figure it out fairly easily in your head, is how many blue seats are in each of these sections. Right, it just says some blue seats. So I'm going to let that be B is the number of blue seats in one section, not all the blue seats in the entire theater. Whenever you're defining your variable like this, it's really important to be specific about exactly what you mean. Notice I didn't just write B equals blue seats. Now, what do you mean by that? Number, right? This symbol right here, you may know it as a hashtag, but us old people think of it as number. All right, so I guess I'll draw a hanger. Not even really sure how I'm going to do this. I'm kind of thinking about this as I go here. So I know that one side should probably just say 88, right? Because I know that the total of this whole thing is 88 seats. On the other side, I'm thinking I'm going to break it into 4 sections because they told me that there's 4 sections. Really, when you draw these things, if the 2 sides are balanced, they should be like about equal length. But mine's not going to turn out that way. But we'll let that slide, right? It definitely looks like the right side of this thing is much bigger and heavier than the left. It's not supposed to look like that, but whatever. All right, and then in each of these 4 sections, there's 14 red seats. So what I'm going to do is I'm going to split each one of these things in half and write 14 on that's supposed to be a 4. 14 for red here, 14 red here, 14 red here, and 14 red here. My pen keeps connecting the top to make it look like 19. It's supposed to be 14. And then the rest of the seats in each of these 4 sections is the blue, right? And B stands for the number of blue seats in each section. So I can just put a B, 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 B here. All right, so there's my tape diagram for this situation. I have a feeling they're going to make me use the tape diagram in the next section. Yep. Okay. And so now it says write an equation to represent this situation. All right, well, let me just use my hanger thing here. I got 88 on one side equals, I'll just add up all that stuff I have there. I have 4 14s, so I can write that as 4 times 14. And I've got 4 B's. Let me write that as plus 4B. When you're going to write a number times a variable, just write number variable. So there's my equation there. I guess I'll write it in the box here. 88 equals 4B plus, what's 4 times 14? 64? So I'll write it like that, 4B plus 64. And what does X represent in this situation? It's what I wrote up here. B, oh, they wanted me to use X. All right, whatever, I can change it to X, that's not a big deal. X represents the number of blue seats in each section. It's important to be specific because it doesn't represent the number of blue seats in the entire theater. It's just blue seats per section. All right, let's hear what do we got here. The Explore. Oh, I haven't looked at how to do these. I hate trying to do these on the fly in the video because they're hard. Let's see here. Drag the numbers so that the values of x are as great as possible. Use the sketch tool if it helps you with your thinking. Okay. So if I need x to be really big, then I probably want its coefficient to be really small. The number I'm subtracting from it to be really big, and the number it equals to be really small, right? So, because in this case, that essentially says x minus 9 equals 0. That means x has to equal 9. I don't think there's any way to get that first one to have an x value any bigger than 9. I could be wrong though. I haven't thought this through. Okay, and then this one. I might want to use a large number here. By subtracting a large number from x, it sort of forces x to be big in order to do whatever you want. I don't know. These are my off the top of my head responses. Let's see what the teacher answers down here say. Okay, so it looks like, oh yeah, silly me. I should have made this an 8. Yeah, because then that forces x to be what, 17. Okay. And then looks like I was on the right track though. You do want a large number in this subtraction here, but they had the 7 available. I didn't have the 7 available because I put it, or no, because I still had my 8, so I put the 8 there instead. And then yeah, it makes sense that you want the other side of the equal sign to be large. That's going to force your x to be larger in both of these cases just because they involve like subtraction and multiplication. So I guess those are the largest ones you can get. In this case, x is going to be 17, right? And in this case, x is going to be 10. Yeah. All right, there it is.